Welcome back. So this is the 8th lecture of mathematical physics, and today we're going to finish the chapter on complex numbers. So let's do a quick recap. So last time I've introduced you to complex numbers, and I've shown you how you can represent a complex number in different ways, in the regular x plus iy, which is the rectangular form, and r e raised to I theta, which is the polar form. And we've seen how, the conversion between these two forms are quite similar to coordinate transformations that we've seen in chapter 1. And we've seen operations with complex numbers. We've seen how to add complex numbers. We've seen the conjugation operation. We've also seen the modulus and the argument functions, which gave you the length of the complex number, sort of to speak, and the angle of the complex number. We've seen how complex numbers can be seen as vectors in 2D space. And we have also seen how to multiply complex numbers and divide them. And we've seen how you can interpret the operations. And not to mention, we have also seen the Euler's identity, the famous e raised to I pi plus 1 equals 0 formula. Well, should I say e raised to I pi plus 1 equals 0, which is supposedly the most beautiful function in mathematics, or the most beautiful formula in mathematics. And we've seen a super useful formula called the de Moivre's formula, which gives you the powers, integer powers, of a complex number. And this is the really compact relation, and this is going to help us a lot in our calculations with complex numbers. And finally, we've seen functions of complex numbers, the exponential, the natural logarithm, and the exponentiation of a complex number to another complex number. Today we're going to do applications on these things that we did last time, and with that we will have finished the chapter. But before that, let's look at a thing or two that we haven't discussed last time. So we've said that from the Euler identity, this relation cosine theta plus I sine theta is true. Now we can use this fact to find relations of cosine and sine with respect to I. So let's see what I mean. So we have e raised to I theta is this, and e raised to minus I theta. So I'm changing theta to minus theta. So how will that change? We know that cosine of minus theta is cosine theta. Cosine is an even function. And similarly, sine of minus theta is minus sine theta. We call sine an odd function. These are just terminologies that you should be familiar from calculus. So using these relations, I can say that e raised to minus theta is cosine theta minus I sine theta, which, if you think about it, is just like taking the complex conjugate of e raised to I theta. I expect to find e raised to minus I theta. I'm just changing I to minus I. Okay, so enough of that. Let's find from these two relations, I want to express cosine and sine with respect to e raised to I theta. So let's do it. If I add e raised to I theta to e raised to minus I theta, this sine and this sine, they'll cancel each other out. So what will I get at the end is 2 cosine theta, since the cosines add up. So I'll have a relation cosine theta equals e raised to I theta plus e raised to minus I theta divided by 2. This is our first relation. Now we've added the two exponentials. Now let's subtract them and see what happens. What do we get? So e raised to I theta minus e raised to minus I theta. So cosine gets cancelled this time, since cosine minus cosine is 0, and sine gets added up. So I sine theta minus I sine theta, which will give me 2 times I sine theta. So from this I can say that sine theta is going to be e raised to I theta minus e raised to minus I theta, the entire thing divided by 2i. This is our other relation. Now these two relations, you have to keep them in your mind. They'll be useful in calculations and integrations later on. I mean, these things will come up a lot, even in other things. Okay, so let's do a few examples based on these relations. Now we have to find, the question is to find cosine the double angle relations using the exponentials representation of cosine. So you're supposed to start from cosine theta, this relation over here. So you're supposed to start with cosine theta equals e raised to I theta plus e raised to minus I theta divided by 2. Okay, let's see what we can do with this. So cosine 2 theta must be related to e raised to 2 theta, 2 I theta. So if you think about it, e raised to 2 I theta will be cosine 2 theta plus I sine 2 theta. So we know that this is going to come up in the expression somehow, right? So since we're clever, we're going to square both sides over here. So what will this give us? Simple, just we'll get e raised to 2 I theta plus e raised to minus 2 I theta plus 2 times this, but you know these are conjugates of each other, so I'll have 0. I mean e raised to 0, and e raised to 0 is nothing but 1, and this entire thing divided by 2 squared. This is cosine squared theta. Now if I simplify this, what will I get? I'll have cosine squared theta times, let's bring this one of these 2's on the other side. So what I'm saying is 2 cosine squared theta equals e raised to 2 I theta plus e raised to minus 2 I theta divided by 2 plus 2 over 2. So I'm just taking, instead of writing 2 squared over here, what I'm saying is that I'll write 1 2 here and 1 2 here, and then I divide these numbers. Now if you look carefully, this thing over here is kind of reminiscent of this, but instead of theta I have 2 theta. So what can this expression be? This is nothing but cosine 2 theta. In general, if you have e raised to I n theta plus e raised to minus I n theta divided by 2, I'll have cosine n theta. I mean, this makes sense. If you expand this in terms of cosine using the Euler formula, this is quite obvious. Okay, so what is the relation I get at the end? What I get is cosine 2 theta plus 1. So if I equate both sides, I'll have cosine 2 theta equals 2 cosine squared theta minus 1. And this relation, we very much know, is true. Okay, now let's do another example from this. The question is to show that d by d theta of sine theta is cosine theta. But you're not allowed to use limits like you did in calculus 1 or calculus 2. Instead, you're asked to prove this starting from sine theta equals e raised to I theta plus e raised to minus I theta divided by 2i. You're starting from this. So what do? I differentiate both sides with respect to theta. And you know, exponential, if I have an exponential function, d by d theta is simply e raised to theta. Or you can use the chain rule, depending on the exponent you have. So in this case, I clearly get d by d theta of e raised to I theta is I times e raised to I theta. And similarly, I'll have minus I times e raised to minus I theta. I'm just getting this down, these two factors down from the chain rule. And this whole thing is divided by 2i. So what will this give us? So if I cancel I from both sides, I've made a mistake here. Sorry about this. This should have been minus because the sign relation, if you remember, had a minus sign. And so this will be plus instead. This was a mistake. So if I cancel I on the numerator and the denominator, I'll have e raised to I theta plus e raised to minus I theta divided by 2, which is again the cosine function. So at the end I have d by d theta of sine theta equals cosine theta, which is, trivial, but then, it's nice to see that our relations here actually give us the same results. Okay, so now let's do some more applications, but this time we'll do applications on powers and roots of complex numbers. So let's get started. The first example is, so the first example is going to be, let me motivate the example first. Let's start with motivations here. So suppose I have 1 squared. Suppose I have 1 squared and I want to find the square root of this. Square root of 1 squared. Well, let me put this question the other way around. Suppose I have 1. So what number squared gives me 1? I want to solve for x. Now you know that minus 1 squared equals 1 squared equals 1. So the solution for x is plus or minus 1. And similarly, if I ask you to find me the cube root of 8, what will you do? Cube root of 8, as you might say, is 2. But remember, I told you something about the fundamental theorem of algebra, which says that, if you have a function of the form x minus a the whole raised to n, where n is an integer, you're guaranteed to have n zeros. This is equal to 0. You're guaranteed to have n zeros that are unique. Possibly the same, possibly identical sometimes. When you have equal roots. So an example of that would be 4. So you can have the identical roots possibly. So that would be x minus 2 the whole squared equals 0. So in that case, x is equal to 2 and 2 is repeated. So including that case, you'll have unique roots. So if I ask you to solve for x cubed equals 8, you'd expect to have 3 different solutions. But we just have one solution here. Where are the other 2? A cubic is supposed to have 3 unique solutions. This is a solution, if you think about it. This cubic is guaranteed to have three unique solutions, or at the least identical solutions. But where are the other solutions? Now this is where complex numbers comes in, and with complex numbers you can find the other solutions because the other solutions are complex basically. Let's look at this from an example. So suppose I'm giving you the same example, cube root of 8. Find me the cubic roots of 8. Now, the first step is to say that, z equals 8, where z is a complex number. The first thing that I have to do is convert 8 to polar coordinates or polar form. How do I do this? Simple. So r is square root of 8 squared plus 0 squared, since you have 0 imaginary part, and this is nothing but 2 square root of 2. And theta, what is theta? Theta is simply tan inverse of y over x, which in this case is tan inverse of 0 over 8, and this is simply 0, isn't it? So I have z equals 8 equals 2 square root of 2 e raised to 0. But I'm kind of lying in here because, I can add 2 pi to this, can't I? Because if I'm on a circle, you can imagine that if I have a circle like this, and this is my theta, if I add If I add 2 pi to this theta, I'll just return to this point. And I can not just add 2 pi, I can add 4 pi, I can add 5 pi, 6 pi. If you add any multiple of 2 pi, this relation is still valid. This is the same theta. So this theta can be represented, as we said, by theta or theta plus 2 pi. In general, 2 pi n, theta plus 2 pi n. So I must account for this. So I must also add e raised to I 2 pi n. Okay, so now we are ready to take the cube root. So by taking the cube root, I mean raising it to the power 1/3. So I'll raise this 2 square root of 2 to the power 1/3. And similarly, I'll raise e raised to 2 pi n, I 2 pi n over 1/3. Now remember, we need 3 roots exactly. So I claim that it's going to be enough for us to consider n equals 0, 1, 2. If we take 3 as well, we'll find that we just return to the value at 0. Now let's see how this is in practice. But first, 2 is square root of 2 times square root of 2. So 2 times square root of 2 is square root of 2 cubed. So cube root of 2 root 2 is simply square root of 2. So this is square root of 2 basically. So z to the power 1/3 is square root of 2 times e raised to 0, or this is when n equals 0, or square root of 2 times e raised to I 2 pi over 3. This is when I take this when n equals 0, this is when n equals 1, or I can take n equals 2. So in that case, I have square root of 2 e raised to I. 2 times 2 is 4, so I have 4 pi over 3. Now you can simply plug these values in your calculator and you'll get the answer. There's no magic behind this. So let's denote, when n equals 0, I denote the cube root as z0. z0 is simply square root of 2 times e raised to 0, which is simply square root of 2. And when n equals 1, I have z1, 2 pi over 3. I just plug this into the calculator. I have square root of 2 cosine 2 pi over 3, which is, I believe, 150, I guess, in degrees, and sine 2 pi over 3. No, it's 120 degrees, I'm sorry. And you'll find that this is simply square root of 2 times minus 1 over 2 plus I and it turns out I have a mistake. Okay, so let's look at what the mistake is. I've said that the square root of 8 squared is 2 root 2, and this is a really big blunder. Square root of 8 squared is obviously not 2 root 2, it's actually 8. So, but our theta is the same because 0 over 8 is still going to give us the same result. This is fine. Okay, so where do I have to make changes? I have to make changes here, 8, and this is 8 as well. And similarly here I have to make, and cube root of 8 is 2 root 2. So I'll just have to add a 2 here, 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 and here. And cube root of 8 is not 2 root 2, it's just 2. Okay, so I have to remove square root of 2 everywhere. Okay, mistakes happen. They don't break the world. Okay, so I sine 2 pi over 3, which is square root of 3 over 2. Okay, so I'll have minus 1 plus I square root of 3. And when I have z2 n equals 2, I'll have 2 times cosine 4 pi over 3 plus I sine 4 pi over 3. And this is going to give me, again, minus 1 minus I square root of 3. You can check these results. You just plug in your angles in the calculator. But one really big note here is that when you choose the argument of z, you should always choose it between 0 and 2 pi. And then you add 2 and pi. If you're using, minus pi to pi, for example, you cannot choose n equals 0, 1, 2, up to n minus 1, where n is the root, I guess, the nth root of z. Let's make it a different letter, mth root of z, m minus 1. So if you're using range minus pi to pi, you cannot use n equals 0, 1, 2, 3. Maybe you have to use n equals minus 2, minus 1, and so on. So, to keep things simple, always choose an angle between 0 and 2 pi. This is the primary argument. These 2 n pi's, these are the secondary ones. These are the secondary arguments. So you can use n equals 0, 1, 2. I would recommend that you don't use negative angles. You should always convert to 0 and 2 pi. And also, this is the first note. The second note is always use degrees or radians. Don't mix up between the two. If you're using degrees, stick to degrees. If you're using radians, stick to radians. So you're not, making mistakes. And a third note, always, make sure that you don't make silly mistakes like this. Like saying that square root of 8 squared is 2 root 2. Okay, so, lessons are lessons. Hope we don't have to learn the lessons again. Okay, let's do the second example of this type. This time, I'm asked to find the 6th root of minus 8i. Okay, same thing as before. I take the first step, z equals minus 8i, and then I convert this to polar coordinates. And this time it's quite obvious. I have 8 e raised to minus I pi over 2. Everything's cool, right? You can see this. I have my vector is pointing downwards because it's minus 8i, and I'm moving minus pi over 2, right? Well, you'd be wrong. I'll tell you why. Because I've used minus pi over 2 here. I've told you just seconds ago that you should always use angles in the range 0 to 2 pi. In this case, if I continue using minus pi over 2, I'll get in trouble when I use n equals 0, 1, 2. I mean, you can technically use minus pi over 2. I'm not saying it's wrong. It's just that you have to find your n will be messy. n into n pi. So let's see what angle we should choose instead of minus pi over 2. We should choose this angle instead. Pi over 2, 3 pi over 2. So I have 90, 90, 90. So you can either use 270 degrees or 3 pi over 2. So this is wrong here. I should use 3 pi over 2. Okay, that was a test. I hope you didn't fall for the trick. Okay, so what is the argument here? As usual, I have to add e raised to 2n pi with an I. So if I take the sixth root, I mean 1 over 6, z power 1 over 6. And this is simply cube root of 2, square root of 2 cubed, the whole thing raised to 1 over 6. And what will I have? What else will I have? No, this is not the cube, square root of 2 cubed, it's 6, because square root of 2 cubed is 2 root 2, and if I square this whole thing, I'll have 8, right? Okay, so that was a quick check, and I have e raised to I 3 pi over 2 divided by 6 times e raised to I 2n pi divided by 6. So in the end, I'll have square root of 2 e raised to 3 will get cancelled with 6. So I'll have I pi over 4 times e raised to I n pi over 3. Now, since this is the sixth root, which values of n do I need? I need 6 values starting from 0. 0, 1, 2, 3, 4, and 5. I have 6 values. And if I substitute n inside here and use Euler's formula, e raised to I theta equals cosine theta plus I sine theta, I'll add an n here. So if I substitute for n equals 0, 1, 2, 3, and so on, I'll get my result. And if you want to check your results, you can plug your values in the calculator. Your calculator won't lie. At least if you remember to use radians and degrees and stick to them. And you can continue as before. Now let's visualize what's really happening in here. Why does this give us the right values? So the complex number, this is the real axis, this is the imaginary axis. And if I have a z, a complex number like this, z, what does taking the square root mean? Taking the square root, taking the nth root, means slicing the circle into n equal parts. So suppose if I'm taking the square root, I'm dividing the circle into 2 equal parts, like this. So this is z1, this is z2. Or if you're following the n values like this, you'll have this is z0 and z1. Now, similarly, if I'm taking the third root, the cubic root, I'm dividing this circle into 3 equal parts. So I'll have angles like, you can see visually that these are all 120 degrees. And so on and so forth. Like taking the square root or the nth root, it's like taking a radius, a circle of radius of modulus z in the complex plane and dividing it into equal parts. This is what it means graphically to take square roots. Now let's look at a concrete example of this. Suppose I'm given a function like, suppose I'm asked to evaluate this thing. This is another example. So I'm asked to find the cube root of 2i minus 2. Let's visualize this graphically. So I have, what is the radius of this circle? To find the radius, I find the the magnitude squared of this complex number, which is square root of 2 squared plus 2 squared, which is square root of 8. So I have 2 square root of 2, or square root of 2 cubed, as you like. So I'll have a radius of square root of 2. And if I look carefully, this is minus 2, real is minus 2, and complex is plus 2. So I have a vector or a complex number going like this. And similarly, as we said before, we want to divide the circle into 3 equal parts. If this is z0, z1 will be like this, z2 will be like this. Let's see if we can actually, find the angles graphically. Can we read off the angles graphically? Let's see. I have 2 and minus 2. So these two sides are equal. So this must be 45 degrees and 45 degrees in here. So I have 90 plus 45. This angle is 135 degrees. So if you have the cubic root, we said that the theta must be equal to 120 degrees between the different complex numbers. So this angle must be 120. This angle must be 120. So let's do this. I have 135 degrees plus 120 degrees, which is 255 degrees. And then I have 255 plus 120, which is simply 375 degrees. This is nothing but 365 plus 10 degrees, if I'm correct. Yeah, makes sense, 10 degrees. So this will be slightly over here. My figure is a bit wrong, but you get the idea. This is just a graphical way of doing things. You're not forced to do it graphically. Usually I would recommend that you follow this method of using ends directly. So in this case, what will I have? I have z equals minus 2 plus 2i. So this will be equal to, as we said, square root of 2 cubed e raised to minus I, pi minus pi over 4, which is 3 pi over 4. There's no minus, I'm sorry. Times e raised to 2 n pi. And so if you want to take the cubic root, or 1/3 power, I'll have square root of 2 e raised to I pi over 4, e raised to I 2 n pi over 3. And you substitute for n equals 0, 1 and 2, and voila, you're done. Plug these values in the calculator and you'll have your roots. I'll not do the calculations. You can do them on your own and find the results. Honestly, you're free to skip this because this is so trivial, but make sure you at least do 2 examples of this type, because you're definitely guaranteed to have a problem of this type in your second test or in your final. In fact, you'll have them for sure. And so let's move on to the next example. Okay, this one is asking you to find len of 1 plus I over 1 minus I. Okay, so let's do this. First, if I want to find the len of a complex number, what do I do? Obviously, I convert it to polar coordinates, r e raised to I theta. But I should remember that this theta can be theta naught plus 2n pi, where n belongs to an integer. But usually, if you're just asked to find one value, just evaluate this. If you're asked to evaluate this and not list the functions, most general form, you can just take n equals 0. That's fine. But you should keep in the back of your head that this is always modulo 2 pi, as they say. Modulo 2 pi. meaning if you add multiples of 2 pi, you still get the same result, because e raised to 2i n pi is always 1. If you multiply 1 to z, you always get z. You should always keep this in the back of your head. And so let's find 1 plus I over 1 minus I. How do I find this, the polar form of this? First thing, I need to express this in the standard form, which is in x plus iy form. To do this, I multiply both sides, both the numerator and the denominator, with the complex conjugate, which is 1 plus I. So in the numerator, I'll have 1 plus I squared. In the denominator, I'll have 1 squared plus 1 squared. These calculations should be familiar with you. So I'll have 1 squared minus 1 plus 2i, the entire thing divided by 2, which is simply I. So I have ln of I. And I, if you remember, I is simply here. This is I, and you have 90 degrees or pi over 2 radians. This is simply e raised to I pi over 2. This should come to you naturally, because I have pi over 2 radians, and this is pointing straight up in the imaginary axis. So this is e raised to I pi over 2, straightforward. You should be able to do this without any calculation. Okay, so I have ln of I, which is ln of e raised to I pi over 2 times e raised to 2 n pi, remember. Okay, and since I just need one value here, ln of this, evaluate this, I only need one value here, so I'm safe to take n equals 0. So in this case, ln I is simply ln e raised to I pi over 2, which is I pi over 2. As simple as that. If you included 2n pi as well, what would you have gotten? You would have gotten, you have an I missing here, plus I to n pi, where n belongs to an integer. Okay, so next thing they're asking you, this part of the same question, calculate sine I ln 1 plus I over 1 minus I. This is the second part. Okay, we calculated this thing, sine of I times I pi over 2 plus I 2n pi. 2n pi won't make a difference, because sine of something plus 2n pi gives you the same result. So you can ignore it safely. This is sine I times I is minus pi over 2, and this will give you minus 1. Simple enough. Now let's do another problem, and this one is going to be sine pi over 2 plus I ln 2. Okay, now where do we get started? Do we have a formula for sine of a complex number? Apparently we don't. So what do we do here? What else do we know about sine? We know that sine of theta is e raised to I theta. This is the equation that we took earlier today, times e raised to minus I theta over 2i. Okay, let's substitute for theta equals pi over 2 plus I ln 2. What will it be? I have sine of theta equals e raised to I pi over 2 plus I ln 2 plus e raised to minus I pi over 2 plus ln 2 plus I ln 2 divided by 2i. Now I can just take e raised to I pi over 2 to be, e raised to I pi over 2, as we said, is I. So e raised to minus I pi over 2. If you go the other way, so if you go the other way like this, minus 90 degrees is minus I. So I'll have minus I. Oh, again, I made a mistake here. This should have been minus. So I have I. Okay, so what's e raised to I ln? I have two i's, remember? I have one I outside, one I inside. So I'll have e raised to I squared ln 2, which is e raised to minus ln 2. And this is simply minus 2. This is simply minus ln 2. If I take the minus inside, one of the properties of ln is 2 raised to minus this minus will be exponentiated inside the len. So e raised to len 2 raised to minus 1 is simply 1 over 2. And similarly, e raised to minus I squared len 2 is e raised to len 2, and this is simply 2. Using these things, I'll have e raised to I pi over 2 is I, and e raised to I squared len 2, this thing is 1 over 2 minus e raised to minus I pi over 2 is minus I, so this will become plus I, and e raised to len 2 is again simply 2, and I have this whole thing divided by 2i, this 2i. So sine theta is going to be simply 1 over 4, I'm just bringing this inside here, 1 over 4 plus 1, which is 5 over 4. This is sine theta. But hold on a second, this is 5 over 4 is 1 plus 1 over 4. Sine theta here is greater than 1. Didn't we, when we were studying sines and cosines, sine was always limited between minus 1 and 1, right? Because sine went something like this. Maximum was 1, minimum was minus 1. But you should keep in mind that this is an imaginary input. You're taking the sine of an imaginary number. So in fact, sine of z does not belong to minus 1 and 1 in general. You'd be surprised. Sine of z actually ranges all the way from minus infinity to plus infinity when z is complex. Sine is not even bounded in when you include complex numbers. Okay, this is an interesting remark. Now let's move on. What do we have now? Okay, I'll do an example now on raising a complex number to another complex number. So I have 1 plus I root 3 divided by 2 raised to I. I'm asked to evaluate this. Again, evaluate is code word for taking n equals 0 when you have 2n pi. Since you only need one value, it can be anything. So let's work this out. So if you're clever enough, you'll see that cosine of 60 degrees or pi over 3 is 1 over 2, and sine of 60 degrees is square root of 3 over 2. These are the things that you have here. So this number is simply 60 degrees is nothing but pi over 3 radians. So this number that you're given here, let's call this z. Z equals e raised to I pi over 3 raised to I. How do I calculate this? First thing that I have to do is take len, natural logarithm on both sides. This is going to give me I len e raised to I pi over 3. But I have to also consider the fact that this pi over 3, I can add 2n pi to it, and I'll still get the same result, this number in here. Again, I've just looked at this expression and I recognize cosine 60 and sine 60. If you recognize this, straight away use it. You don't have to convert to polar coordinates and fiddle around with equations. Okay, so 2n pi, I 2n pi times I. So I have len z times I equals I times I pi over 3, because len of e raised to I pi over 3 is I pi over 3, and I'll have, since these two are multiplied, and len of xy, this is just a reminder, equals len x plus len y. This is just a reminder. This is x, this is y. So I'll just add them. When I take the len of these things, I'll just add them together. Okay, so I'll have I 2n pi, and if I multiply these things, I'll have minus pi over 3 plus, I'll have a minus here as well, minus 2n pi. This is len z. How do I find z from here? Z equals e raised to len z, and this is simply going to give me e raised to minus pi over 3 times e raised to minus 2n pi. And since we said this is just an evaluation, I can take n equals 0 and it won't make a difference, And so our final result is z equals e raised to minus pi over 3. Done. Okay, that's enough examples for complex numbers. These should be, if you practice questions similar to this, at least one of each type, I think you'll be safe. I mean, you only expect to get 1 or 2 questions from this in the tests and in the final. Okay, so with this we have finished the chapter on complex numbers, and now we're going to move on to a new chapter. A new chapter means I need to open a new notebook. And this chapter, I've named it The Twists and Turns of the Fourier Series. And we're going to explore, in today's lecture, we're not going to do the Fourier series. We're not going to, do it properly. I'm just going to motivate the Fourier series, because Fourier series is such an important concept in physics that it deserves a motivation. So you see why Fourier actually thought of this. So the Fourier series historically was discovered by Joseph Fourier in the early 1820s while he was studying heat flow equation, which is a very physical problem. And his motivation was as follows. The heat equation goes something like this. This is the Laplacian of U. U is some quantity. You can consider U to be the temperature. Okay, equals some constant 1 over alpha times partial t over partial time. So this is partial t over partial time gives you the rate of heat flow, right? And gradient squared of t, this gives you an idea of what is the temperature. I mean the Laplacian of t gives you an idea of the temperature difference between 2 points per se. Say this is at some temperature, this is at another temperature. This is what the Laplacian measures in a sense. So if he could solve it, he could solve this equation like in terms of sines and cosines. And sines and cosines, waves in general in physics, they're usually sines and cosines, right? And waves are basically everywhere. You have sound waves, you have vibration waves. I mean, if I'm knocking on the table, what you're hearing is through vibrations, of course. And even at the most fundamental level, particles are excitations of fields. And particles can be considered as waves as well. So the wave-particle duality. Waves are basically, almost everywhere in nature. So it makes sense that, you want to express your physical quantities in terms of sines and cosines. Now, before I go any further, I want to take an interlude into dimensions. Suppose I give you a vector like this and ask you what is the dimension of this vector. Suppose I'm giving you a vector space. If you've taken linear algebra, you must have come across this thing called vector space. A vector space is simply a vector and all of its combinations. Everything along this line is the vector space. We say that this vector spans a vector space which is a line. Now this thing is in a 2-dimensional space. So I'm asking you, what is the dimension of this vector? Does this question even have a meaning? Well, to be honest, you could argue that this vector is 2-dimensional because you're in a 2-dimensional space and I need 2 numbers. I need ax and ay to specify this vector. So you might argue this is a 2-dimensional vector. But then again, I might argue, because you have taken your basis to be I and j, what if I took this this unit vector, the unit vector along A, to be the basis. In that case, I only need one number, just the length of A times unit vector of A along A. So I might argue that this is a one-dimensional vector. Now, why do I want you to think about dimensions now? I'll come to it in a moment. Now let me ask you the same question. What is the dimension of A? But now I'm putting this in a 3D space, right? What is the dimension of A? I ask you the same question. Again, you might argue this is 3D, right? And similarly, I'll argue again, if I take the unit vector along A, I can just say that this is one-dimensional. This vector space, sort of to speak of, spans a line. The line is a one-dimensional object. So it makes sense that you have a one dimension. This vector space is one-dimensional. Now, what if I put this in a four-dimensional space? Will you say that this is a 4D object? This vector is four-dimensional? Of course not. It's still one-dimensional, but you're putting it in a four-dimensional space. A one-dimensional object in a four-dimensional space. Just like this, I mean, what I'm trying to tell you is that if you have a vector, so what I'm trying to get here is that it doesn't matter how many columns you have, you might have a vector that has many components, but it's still one-dimensional. It's still a one-dimensional object. So if you think about it, if I draw a 2D plane in a 3D space, this vector space is two-dimensional, but it's still embedded in a 3D space. So the dimension of an object doesn't have to do with the space it's in. It can be in an infinite dimensional space. This brings me to infinite dimensional vectors. So I'm talking about vectors which have infinitely many components. So I have A0, A1, all the way to A infinity. What do these vectors actually mean? And, do these vector space even have a meaning? And I'm here to tell you that you have seen infinite dimensional vectors. Where exactly did you see them? Well, functions, f of x equals x squared. And if you plot this, you'll have infinitely many entries. So I can have x squared at 0, I can have x squared at 1, 2, 3, and so on. And even fractional values. I can have x squared of square root of 2, so on and so forth. I have an infinity of points. So if I want to express a vector that has x squared as its components, I need infinitely many points. So I have 0 squared, 0.0001 squared, I don't know, pi squared, e squared, and so on. It'll take me infinitely many components. But this whole thing is actually one-dimensional in a sense. Like this, you have infinitely many components, but at the end of the day, you're just expressing one piece of information. That is f of x equals x squared. This brings us to vector spaces using infinite dimensional basis. So I want to motivate this by going you through the 2D space. In 2D space, you had bases I and j, right? So in 3D space, you had bases I, j, and k. From linear algebra, you have probably heard of span. The span of a vector space is related to the dimension and the basis. So you can span an n-dimensional vector space if you have enough bases. If you want to span an infinite dimensional vector space, so I have many axes, so at this point it doesn't even make sense to draw a figure like this. So I need infinitely many bases vectors. And why am I talking about infinite vector spaces? And have you ever seen infinite vector spaces? Like, why am I talking about this? And the answer is, you have seen infinite vector spaces. So you've seen the Taylor expansion of functions, which is a0 plus some coefficient a1 times x raised to 1 plus a2 x raised to 2 plus a3 x raised to 3, and so on. You have a polynomial of infinite order. So what you are doing there without even knowing is expanding a function in polynomial basis. Your basis vectors I, j, and k, they are 1, x, x squared, x cubed, and so on. Polynomials. Now, from linear algebra, you know that I, j, and k are not unique. I can have I plus j, j plus k, k plus I. The basis is not unique. And I can switch between I and j and k and I plus j. I mean, I can switch between these two. One is not, more preferable than the other. Maybe I, j, and k is easier to work with, but it's not the only basis. Similar to how, coordinate systems, like you have ER, E theta, and E phi. For 3D space, I can use any of these interchangeably. So so the space, if I have a vector in a space, remember in our first lecture that I said a vector is something that exists on its own. It doesn't depend on the coordinate system. It doesn't depend on what basis you're using. It can be this basis, it can be spherical basis, cylindrical basis. No one really cares. And similar to this, polynomial basis is not the only basis available to you. You have cosine and sine basis as well. But we need infinitely many cosines and sines. We cannot just, span an infinite dimensional vector space using just two functions. So we'll have cosine nx and sine nx, where n is an integer. So this is the motivation behind Fourier series. You're trying to express a vector and an infinite dimensional space using basis of cosine and sine. And this is similar to expanding a function in a Taylor series. So in a Taylor series, you have sine of x equals 1. You have x minus x cubed over 3 factorial, and so on. The idea behind Taylor series is that these coefficients, you can find them using some formula. So I can find the nth coefficient using the nth derivative of sine at 0 divided by n factorial. This is the coefficient, right? The n factorial won't appear because we've already included it. We have a way, we're assuming a polynomial form of sine, and you have a method of finding these coefficients a1, a2, and a3, and so on. Fourier, he proposed that we use sine and cosine as basis. And the motivation behind this is, as I said, you have many physical phenomena, they are waves, and sines and cosines are the usual way you express waves. And solutions to differential equations, simple harmonic oscillator, and so on and so forth, they have sines and cosines in them. And if you know the solutions of sine and cosine, and I give you any random function, I can find you a solution in terms of sine and cosine. That is the motivation behind Fourier series. So you have a very complicated vector space, and you have basis vectors that are really hard to deal with. So you make a change of basis. In the same coordinate system, I choose a convenient coordinate system, a convenient basis, like I, j, and k. I, j, and k are orthonormal. And orthonormal bases are, easiest to deal with. If you have an orthonormal basis, you can expand any vector I give you in terms of these components quite easily. Right? So this is the motivation. Cosine and sine makes it easier to solve differential equations. So one of you asked me about, can we deal with, differential equations, say of the form d squared minus d plus b times f equals g of t, for example. I answered at the time that if you have g of t, sine, cosine, or an exponential, you can solve it using simple methods like operator methods. But if you have a function like g of t is, I don't know, x cubed plus 4x, this would be in terms of t. In that case, you're really in trouble, because there is no known solution of this response. This is a non-linear equation. This equation becomes non-linear in that case. So what do? We take this g of t, we find a Fourier representation of it. So in terms of a cosine plus b sine, and so on. You have infinitely many terms. You have cosine x, sine x, you have cosine 2x term, sine 2x term. You have infinitely many of these. And Fourier figured this out. It's not really trivial if you think about it. Unlike I, j, and k, it's not obvious if I can expand any function with respect to cosine and sine. In a sense, I don't know if cosine and sine spans the infinite dimensional function space. So we're dealing with function spaces here, function spaces which are infinite dimensional. So this is the motivation behind this. Since I know, cosine, the solutions when you have cosine and sine, I can simply, by superposition, since I have if I have a cosine, g of t equals a cosine plus b sine, and I know the solutions to this, I can just multiply a and add it to this solution. So I'll have infinitely many terms, but now I know how to solve this. I know this sounds, a bit vague in a sense, because we're not really solving an actual problem, but I'm trying to motivate to you why, we study Fourier series. And by the way, Fourier series is not the same as Fourier transform. Why is that? Fourier series, I just explained to you this idea. It's like a change of basis. You're changing from one basis, from a function of, I don't know, x equals ln x or x squared or a polynomial. You're changing from one basis to trigonometric basis, sine and cosine. And transformation is something entirely different. Fourier transform of a function gives you another function. So if you have a function in time, you'll get a function back with respect to omega, the angular frequency. This is what Fourier transform does. Fourier transform is like a machine. It's like it's like you're changing the space itself. So if I have, say, x, y, and z, the reals, I'm just giving you an analogy here. I'm changing it entirely. I'm changing the space entirely. I'm changing it to x prime, y prime, and z prime. The axes are changed now. But in this case, Fourier series, I'm not changing the space itself. The vector is still the same, but in this case, if you have a vector, even the vector will be changed. Do you understand? In this case, the vector is still the same. The vector is not changing. Instead, I'm just changing the basis. Before, if the basis was like this, I'm now changing the basis to be different basis like this. And luckily or unluckily, you'll not be dealing with Fourier transform in this course. You'll only be dealing with Fourier series. But you should actually study Fourier transform later, because it's going to be needed for quantum mechanics next semester if you take it, and possibly in EM. And if you study, electronics too, maybe you need Fourier transform. And, depending on who teaches you, you'll also need it in optics, Fourier transform. So, even Fourier transform has a meaning. You can solve a differential equation using Fourier transform. Anyway, these are all, methods of simplifying your differential equations and, to deal with your problem in a much smoother way. Okay, so now I have to consider if I want to continue with the derivation of Fourier coefficients with you. Since we've actually gone over time, I'm going to stop right here. In the next lecture, we're going to derive the Fourier coefficients, and we're going to solve some examples on Fourier series. And this is one chapter in the syllabus where I cannot really help you a lot, because I can show you how to derive the formulas. I can help you understand where these formulas come from, but to do the actual calculations, you have to be really really comfortable with doing integrals. You have a lot of integration by parts and so on, so you have to be comfortable with doing integrals, and for this you need a lot of practice. But you don't have to worry a lot, because once you get the hang of integration, there isn't really a lot of things that are difficult here. Okay, so thank you very much for listening, and I'll see you next time.